So you have a second chance to. The next quiz will be June 5th. It's going to be just 1 hour quiz, and after quiz, we are going to have a class. So 1 hour quiz. So whatever we covered after the linear algebra, so some derivative part and the topics covering today and next week. And next week, actually, is going to be online class. I have to attend some other meeting in the government, so I'm going to put the next week's class on YouTube. So, 여섯 번째죠. So it's going to be 6th and 7th class will be the topic for the next quiz. It's just 1 hour. So just prepare 1 page. It's basically just how to obtain the derivative and the first order differential equations. So I think we were doing some composite functions, like when y is f to gx, then dx dy is, dgx, dy, dx, dg. Derivative of composite function is the chain rule. And when y is fx times gx, then I think we have derived these 2 results previously, right? And maybe in high school days you just memorize the results, but we have shown how to obtain these results. But now you can go back to your high school days and just memorize it. But we have shown how to do that, right? So for example, y x is secant x is 1 over cosine x. So we can set gx as a cosine x. Then dg d 1 over g is what? Simply minus g square, right? 1 over g square. And dx dg is minus sine x. So dx d secant x is actually minus g square minus sine x is cosine square x sine x, which is cosine x sine x 1 over cosine x, right? So this is tangent x secant x. Interesting case is y is tangent x. This is cosine x, sine x. Or you can write as a sine x times secant x. Then dxt tangent x dxt sine x secant x plus sine x dxt secant x. So what happens if you differentiate sine x? You obtain cosine, right? So this is cosine x times secant x plus sine x times, we just have done the derivative of secant x, which is tangent x secant x, right? Tangent x secant x. So cosine x secant x is what? 1, right? Sine x, sorry, cosine x, sine x, sine x, secant x, 1 plus cosine square x, sine square x. So which is cosine square x plus sine square x. What happens to if you add cosine square x with the sine square x? What do you get? This simply 1, right? So this is secant square. 1 over cosine square x is secant square x. So let's summarize two results. To look at the previous result, then if you differentiate tangent x is secant square x. Let's see, am I loud enough? I mean, can you hear me well? So that's very interesting case that copy. Am I going a little too fast? It's okay. dxt secant x is secant x tangent x, right? dxt tangent x is, what do we get? Secant square x, right? I mean, if you, what happens if you add them together? dxt tangent x plus secant x. That's secant x tangent x plus secant square x is secant x. You can combine them together. Oh, tangent x plus secant x. Uh-oh, something very interesting, right? This term and this term are the same, right? So if we divide them by tangent x plus secant x on both sides, we get tangent x secant x dxt tangent x plus secant x is secant x is 1 over cosine x. This is very interesting result. That, all right. Oh. What happens to dx, d, ln, fx? This is dfd ln f dxt fx, right? And what happens to if you differentiate log f by f? You obtain 1 over f. Right? And in summary, this is a very interesting form. It does have a name that logarithmic derivative. It's called logarithmic derivative. The previous example is a typical case of a logarithmic derivative. That it's a good example, right? Tangent x, secant x, dxt, tangent x, secant x. This is nothing but dxt ln tangent x plus secant x 1 over cosine x. So this is a very good example of a logarithmic derivative. And actually, the first order differential equation can be solved mostly by using this logarithmic derivative. Let's do a differential equation. Its definition is a set of equations containing derivatives. So there can be different kind of derivatives like a dx, dy. Sometimes y prime. This is called first order derivative. Dx square, d square y. Second order nth order derivative. This is a linear case. However, sometimes we have y square, right? This is second degree first order derivative. Y to the n to the m, mth degree, nth order derivative. This is called nonlinear case. In nonlinear differential equation is much more difficult to solve. But this method, we are going to cover only the linear case. It's good news, right? We will be focusing on the linear case only. Assuming you have a differential equation, this is not a trivial problem, right? That you know the answer already. You know that we know. Right? So y must be log tangent x plus secant x plus some constant. Maybe you can consider another logarithmic derivative. How about this? X plus square root of x squared plus 1 this is 1 plus twice of x squared plus 1 times 2x, right? This is square root x squared plus 1 x plus square root x squared plus 1. So this is another logarithmic derivative that x plus square root x squared plus 1 over dxt x plus square root x squared plus 1, right? So this is nothing but dxt ln x plus square root x squared plus 1. So if we have another very simple differential equation, maybe I'm going a little too fast. So if, okay. If that is a problem, you know the answer immediately if we know the logarithmic derivative, right? We know that y should be ln x plus square root x squared plus 1 plus c, right? So many of the problems when non-trivial, then look for the logarithmic table. That's the solution. Suggest. So where do you find the logarithmic table derivative? There is a CRC. 매스매티컬 핸드북인가? 이름이 뭐지? table. Let me Google it. There's a CRC table, and you can find the PDF form. Let me check the Google. CRC standard tables and formulas. PDF. So if you search for CRC, standard mathematical tables and formulas in Google, and maybe you can find PDF file, PDF form. And I think if my memory serves, they contain about a little over 1,000 logarithmic derivatives. 이거 PDF 파일 있지, 구글에. So for the next quiz, I'll allow you to bring this PDF file as well. So you can prepare one-page cheating sheet and this paper, so that I'm free to choose problems as difficult as it can be for the first order differential equations. So search for Google, and you can actually download the PDF file, I think. Or, I don't know how much it is, you can order from Amazon. Let me see how much. Actually, if I were you, I would buy one. And also get the PDF, because this CIC is very $75. I'm a little bit too expensive. Maybe just download the PDF. Actually, you can find some used one that's about $10. It's not that bad, right? The 75 is a bit stiff. So this is a very standard case and easy case, but what if? What if? Problem is complicated, such as dx, dy, pxy equal qx form. This is standard linear first-order differential equation. Standard linear first-order equation. Differential equation. This will be the topic for next quiz, actually today and next week. The idea is you like to transform this equation into dx dzx is qx. Set. 멈췄네. Oh, sorry. I think something happened to the projector was screen that stop. Oh, yeah, no. 뻔뻔 안 먹었네.
이안 나오신 거죠?
My sister got COVID last month. She did it was the first time. She got very sick for a month. Still in this is the reason I'm still wearing mask. 미분하는 거 괜찮아요? Comfortable 해요? Are you feel comfortable with the derivative? Right. So idea is to transform because this form is much easier to integrate, right? How do we transform this into this form? Let's try try zx, some lambda x, yx, and qx as lambda x, gx, small qx. And here lambda x, Greek lambda, is called integral factor. Integral factor. It's called integral factor or integration factor, or sometimes they call integration factor. So I may use some Greek alphabet. So maybe you need to be familiar with some alpha, beta, gamma, delta. How many of you know all the Greek alphabet? It's 24. Okay. Alpha, beta, gamma, delta, eta, epsilon, eta. This is lambda. We know mu, nu, sigma, tau, zeta, psi, etc. Of course, omega. So I may use several Greek alphabets during my class. So the original equation was this: dx dy plus px y is qx. Then we like to transform this into dx dzx equal to bqx, such that zx is lambda x yx, bqx is lambda x small qx. So dx dzx is what? We have dx d lambda x yx plus lambda x dx d yx is equal to lambda x small qx, right? So we divide lambda x on both sides. Then we get what happens. dx dyx plus lambda x over dx d lambda x yx is qx. So we need to compare this with this. These two equations must be identical, right? 1 and 2 should be the same. One must be same as 2. Then what do we get? Px is lambda x over dx d lambda x dx d ln lambda x. Right? So what do we need to do? Find the logarithmic derivative such that it gives px. So solving this equation, so I'm going to repeat that again. So this is very important part. So I'm going to go as slowly as possible. So we have px yx is equal qx, right? And we transform this into dxt lambda x yx equal lambda x qx. So how to find lambda? It's simple. Px is dxt ln lambda x. Or lambda x or lambda x is exponential this is a bit complicated. Again, I'll give you time to copy. So let's consider the next simple case. Okay. We have this equation. So we know that dxt ln lambda x must be cosine x, right? So we know the lambda x already, right? Lambda x. We have done this before. So which logarithmic derivative gives secant x? Tangent x plus secant x, right? We know that. We know that we have done that. This from our knowledge of logarithmic derivative, right? So times 0 is equal to 0, right? So lambda x yx is some constant. So yx is tangent x plus secant x over c. C over tangent x plus secant x. Maybe we can take a break for a few minutes. A bit more complicated case, dx dy plus secant xy equal tangent x. So we have done there are two cases, dx dy plus pxy equal to 0. No, qx. And qx can be 0 or non-zero, right? When qx is 0, it's called homogeneous case. Differential equation. When qx is non-zero, it's inhomogeneous differential equation. So dx dy, so this problem is actually inhomogeneous case, right? So we have transformed this equation into lambda x y equals lambda x tangent x, right? And dxt ln lambda x equal to secant x. So we know lambda x already, right? So lambda x is equal to in this case we know the lambda x, which is tangent x plus secant x, right? How about lambda x times tangent x? Which is tangent x secant x times tangent x. Tangent square x plus secant x tangent x, right? Uh-oh. But we have some knowledge about the derivative. We know that txt secant x is what? Secant x tangent x, right? We know that. How about tangent x? Which is 1 plus tangent square x, right? So what do? We know this. So we can do this, right? Because we know this. We have tangent square x plus 1 plus secant x tangent x minus 1. We can do that, right? The right-hand side is tangent square x plus secant tangent x, right? And we know derivative, right? If you take a derivative of secant x, it will give secant x tangent x. But on the other hand, the derivative of tangent x is 1 plus tangent square x. So we have already tangent square x. So we anything, right? So I apply the principles of doing nothing. Plus 1 minus 1 is equal to 0. So lambda x tangent x is tangent square x plus tangent x secant x is tangent square x plus 1 plus tangent x secant x minus 1, which is tangent x plus secant x minus x, right? Is equal to dxt lambda x yx, which is dxt tangent x plus secant x yx. So now it's relatively easy to solve. Therefore, tangent x plus secant x yx is tangent x plus secant x minus x plus c. So yx is simply 1 plus tangent x plus secant x c minus x. So the solution is relatively easy to find because we already knew the logarithmic derivative of tangent x plus secant x. Probably we need to do another example. We need to have cx lambda x times yx and txt ln lambda x is 1 over square root of 1, right? I just covered the logarithmic derivative, which gives 1 over square root of x cubed plus 1, which is lambda x is equal to x plus square root of 1, right? So, in this case, dx d x plus square root x squared plus 1, y is equal to 0. or x plus the square root x squared plus 1, y equals some constant, or y x plus square root x squared plus 1, c. So first order differential equation can be very easily solved if you know the information of the logarithmic derivative, which is equal to px. So maybe I still need the time to copy. The recipe for this equation, we have dx, dy, px, y, qx, recipe. Number 1, find lambda x such that dx t ln x ln lambda x equal to px. This first step, right? So if that's the first step, you have to check with the CRC table. So given the equation for px, you just look up the CRC table to find the proper logarithmic derivative. Then dxt lambda x yx is lambda x qx. So the time to copy. Now this we have dx dy x squared plus 1 y equals x plus q. So lambda x, step number 1, dx d ln lambda x is equal to square root of lambda x squared plus 1. So we know the lambda x, right? Oh, God bless me. Lambda x is x plus square root x squared plus 1. So dx d x plus square root x squared plus 1 yx is equal to x plus square root of x squared plus 1 times x squared plus x squared plus 1. Luckily, these two cancel each other, right? So we have only x. So x plus square root x squared plus 1 yx is 1/2 x squared plus some constant, and yx is x plus square root x squared plus 1 1/2 x squared plus c. give it time to copy. And let's try to find some other logarithmic derivative. More. Derivatives. We know tangent x plus secant x, right? We have done this. And we have done x plus the square root of x squared plus 1, right? Let's consider, how about cotangent x with cosecant x? That could be another possible combination, I think. So CX is 1 over sine x, right? So dx CX is, can you do that? Minus sine square, right? And cosine x. So that is minus sine x cosine x 1 over sine x is minus cotangent x CX, right? dxt cotangent x is dxt cosine x secant x, right? So dxt cosine x CX plus cosine x dxt CX. Maybe save some space and move this into here. So that is, if you differentiate cosine x, what do you get? Minus sine x, right? And CX minus cosine x cotangent x CX, right? That is minus 1. And this is minus cotangent square x, right? Cosine x times cotangent x times CX is cotangent square. So let's summarize in the next page. Let me check. Cotangent x minus 1. Okay. So another example. Oh, maybe just dxt cotangent x is minus 1 minus cotangent square x. dxt CX is minus cotangent x CX, right? Which is minus 1 minus sine square x cosine square x is minus over sine square x minus sine square x plus cosine square x is minus CSC square x, right? So what do we get? dxt cotangent x plus CSCX is minus CSC square x minus cotangent x CSCX is minus CSCX cotangent x plus CSCX, right? So we have cotangent x plus CSCX over dxt cotangent x plus CSCX is minus CSCX or dxt ln cotangent x plus CSCX is, what do we get? Minus CSCX. This is another possible derivative. And we can design some problems, right? So we have to be careful with the minus sign. So I can give you the problem. Okay. That dx, sorry. Right? And we just found out the logarithmic derivative. What is lambda? It's cotangent x plus secant x, right? Number one, find lambda. dxt ln lambda x is minus sin x minus CSCX. We know the lambda already, right? We just found out. Lambda x is what? Cotangent x plus CSCX, right? So dxt cotangent x plus CSCX y is 0. So y is actually cotangent x plus CSCX over c, right? But I can be vicious. But I can modify the problem a little bit. This is quite straightforward, isn't it? But what if dxdy plus sine pi plus x y equal to 0? I can put this way. It's slightly different from mine. What is sine pi plus x? Minus sine x. So I can do some trick. I can be vicious to confuse you, to put extra pi in the argument. But you shouldn't be confused. So this is basically minus sine x, right? Now we have dx dy plus minus, right? Minus cs cxy equal minus cotangent x. Step number 1, we find the logarithmic derivative. We already did. Step number 1, dx d ln lambda x equal minus cs cx, which is lambda x is cotangent x plus cosecant x, right? Now, number 2, dx d cotangent x plus cosecant x y equal to minus cotangent x times cotangent x plus cs cx equal minus cotangent square x minus cotangent x cs cx, right? So what is, we need some result. dx d cosecant x is minus cosecant x cotangent x, right? And dx d cotangent x is minus cotangent square x minus 1, right? So minus cotangent square x minus 1 minus cotangent x cosecant x plus 1, which is dx d cotangent x plus cosecant x plus x, right? So cotangent x plus cosecant x y equal cotangent x plus cosecant x plus x plus c. So y is equal to 1 plus cotangent x plus cs cx x plus c. Perhaps you can find the logarithmic derivative involving what? Hyperbolic functions. Let's see if we can find some logarithmic derivatives involving hyperbolic functions. Can I move on or a little bit too fast? Hyperbolic functions. cosine hyperbolic x is exponential 2x plus minus x, and sine hyperbolic x is 2 over exponential x minus exponential minus x. So d cosine hyperbolic x is actually sine hyperbolic x, and d sine hyperbolic x is cosine hyperbolic x. d secant hyperbolic x is d 1 over cosine hyperbolic x is minus cosine hyperbolic x square sine hyperbolic x is minus tangent hyperbolic x times secant hyperbolic x. Right? dx tangent hyperbolic x is, let me see, it's dx sine hyperbolic x times secant hyperbolic x. So this is cosine hyperbolic x times secant hyperbolic x times sine hyperbolic x dx secant hyperbolic x is 1 plus sine hyperbolic x times minus tangent hyperbolic x times secant hyperbolic x. Oh. Perhaps I just need to copy this part. Copy. Next page. Let me double check if I made any mistake. Minus. Paste. Nice, right? So this is 1 minus cosine hyperbolic x sine hyperbolic square x, which is cosine hyperbolic x cosine hyperbolic square x minus. What is cosine hyperbolic square x minus sine hyperbolic x? 1. So dx d secant hyperbolic x is minus tangent hyperbolic x secant hyperbolic x, right? If we add them together, what do we get? Dx d tangent hyperbolic x plus secant hyperbolic x is secant hyperbolic x minus tangent hyperbolic x. Secant hyperbolic x is secant hyperbolic x secant hyperbolic x minus. So lesson number 1, you cannot obtain logarithmic derivative out of hyperbolic functions, right? That's good news. You don't have to worry about that. Right? So no logarithmic derivative unless I made some mistake. Let me double check. Okay. So this is good news, right? We cannot obtain logarithmic derivative out of hyperbolic functions. So you don't have to worry about that for now. Okay. Probably can stop here today. And next week, just watch the YouTube. I put the YouTube class. And we have maybe 1 hour to 1 hour and a half quiz on 2 weeks from now.